Hi everyone. This video focuses on the topic of inferences about two population proportions. So if we have a situation where we are interested in the difference between proportions from two different populations, this is the topic that we're talking about. So say for example, we are looking at the proportion of investors in Ontario who invest in safe investments such as GICs, guaranteed income certificates. And we wanted to compare that to investors in Nova Scotia investing in the same instrument. So we could look at all the investments in Ontario and the proportion that use GICs, and then all investments in Nova Scotia, and see the proportion that actually use GICs, and determine whether or not one market compared to the other has a higher proportion of investors who invest in GICs. So if, for example, you're a company that is selling GICs, where should you invest? Or where should you actually set up? Should you set up in Nova Scotia or should you set up in Ontario? And so this could help you answer that question. So as we say, we have two populations. Each population has a proportion, say P1 and P2. Okay? So if we have each of these populations with P1 and P2, we could take samples from P1 and we could take samples from population 2. And then in those two samples that we take, we will observe a sample proportion, P bar 1, P bar 2. And when we subtract those two, we have a sample estimate of the difference between the population proportions, kind of like what we've been doing before. Same thing with the means, right? So that's a sample estimate of, excuse me, the difference between the population proportions, P1 minus P2. So I'm sure you'll agree there that if I keep taking multiple combinations of samples, eventually I will get a sampling distribution of the difference between sample proportions. And then the question that we've always asked is, what is the nature of that sampling distribution? If it turns out that N 1P1 is greater than or equal to 5, and then 1 minus P1 is, let's put P bar, sorry, since it's samples, is greater than or equal to 5. And then we do the same thing for the second population, P bar 2, sorry here, P bar 2 greater than or equal to 5, and then 1 minus P bar 2 greater than or equal to 5. So if we satisfy the conditions for normality for the two populations, or the two samples, sorry, basically, then the sampling distribution of P bar 1 minus P bar 2 will be a normal distribution with a mean of mu P bar 1 minus P bar 2 and a standard error of P bar 1 minus P bar 2. It turns out that the average of the difference between the sample proportions, that is mu P bar 1 minus P bar 2, is just the difference between the population proportions. Kind of like how we said that mu X bar 1 minus X bar 2 was just equal to mu 1 minus mu 2. So it's the same concept right here. The standard error, which is sigma P bar 1 minus P bar 2, is now given by P bar 1. I shouldn't say P bar because right now we're actually assuming that we have the population proportions. So we'll use the population values of P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. Now we know that when we work in with sample data, we don't have the population values, so we'd have to replace those by the sample estimates. But for now, we're basically just establishing the mean and the standard deviation of the population, or we should say, or the sampling distribution of the difference between sample proportions. We're establishing the mean and standard deviation of the sampling distribution of p bar 1 minus p bar 2. All right? And we're saying its mean will be p1 minus p2, and the standard error will be this formula right here, which is the square root of p1 into 1 minus p1 over n1 plus p2 times 1 minus p2 divided by n2, and we take the square root of all of that. So once we have those two parts, we could get a test statistic for hypothesis test, and we could also get the formula for a confidence interval. All right. So once we have that information, it makes it relatively easy for us to do so. So let's see, if we wanted a confidence interval for the difference between population proportions, then what would it look like? So that would be sample estimate, which is p bar 1 minus p bar 2, plus or minus the critical value times the standard error. Now, clearly I cannot use p1 and p2. I have to use the sample values. P bar 1, 1 minus p bar 1 over n1 plus p bar 2, 1 minus p bar 2 over n2. So that is a confidence interval for p1 minus p2. All right? That's a confidence interval. Now, if we're doing a hypothesis test, the test statistic for hypothesis tests involving HO, HA, P1 minus P2 is greater than or equal to, less than or equal to, or equal to 0. If that's the case, then our alternate hypothesis would be P1 minus P2 is either less than or equal, sorry, not less than or equal to, what's wrong with me? Less than or greater than or not equal to 0. All right? So those would be the options for your alternate hypothesis. As you recall, we never have the equal sign in the alternate hypothesis. So what does a test statistic in that case look like? It turns out that the test statistic will look like this. Z observed would be p bar 1 minus p bar 2. Now remember, in the null hypothesis we said that the difference would be equal to 0. That's the either greater than or equal to 0, less than or equal to 0, equal to 0. So when we do the hypothesis test, we will set the difference between the two proportions to be 0. So this will just be 0, which actually leads us to an adjustment that we have to make. I'm going to show you what I'm talking about. So normally we would use the sample estimates, which is p bar 1, 1 minus p bar 1 over n1, p bar 2, 1 minus p bar 2 over n2. Okay? But there's a problem. What's the problem? The problem is that in the null hypothesis, we will assume that p1 minus p2, we will set it to 0, which means that p1 is equal to p2. If p1 is equal to p2, then it's equal to a constant p. We cannot estimate p with two different sample proportions. So look at this. Here we will be using p bar 2, to estimate p, and p bar 1 to estimate p. But then more than likely those are going to be different. So since those are going to be different, we cannot use the sample estimates. We have to use instead a different value. So we need to take off the we need to take those off and replace them with just a p bar. P bar. We call that P bar the pooled sample proportion. Much like we had the pooled sample standard deviation. And we will calculate this pooled sample proportion by taking together the two samples that we got and combining them together. That's essentially what we will do. So in the end, what we will have is we will take the observations from sample 1, let's call it x1, add it to the observations from sample 2, x2, and then divide by the total sample size, which is sample size 1 plus sample size 2. So when we combine those together, we get P bar, which will just be a single estimate, and then we will use P bar to estimate for us P. All right? So that's why we will have this as our test statistic. Whenever in the null hypothesis, we assume that the difference is 0. But what if we don't assume that the difference is 0? What if we don't assume that the difference is 0? Then in that case, we will use the original sample estimates for the test statistic. So in this case, if we have HA, if P1 minus P2 is equal to some value, and P1 minus P2 is not equal to that value, where that value is a non-zero value. What we mean, so for example, if we say P1 minus P2 is equal to 2%, in other words, the difference between them is 2% versus the difference is not 2%. So now 2% is not 0, all right? So in this case, what we will end up doing is having to use a different test statistic, but not all that different, just that we are going to use the sample estimates to work with us in this case. So what we would have is Z0 would be P bar 1 minus P bar 2 minus whatever that value difference is, but we'll just put P1 minus P2, whatever that value. So that P1 minus P2 will be equal to that value that we talked about earlier. And we will use the sample estimate since we don't know what P1 and P2 are, just that we're estimating that there's a difference between them, which is not 0. In which case we have P bar 1, 1 minus P bar 1 over N1 plus P bar 2, 1 minus P bar 2 over N2. And so that's the variation. Notice now I'm not using just P bar in the estimate of the standard error. I'm using the individual sample proportions. Okay? So those are the formulas that we will need to work with the inference around the difference between two population proportions. All right? So I want you to just kind of reflect on that a little bit, that we are interested in the difference between two population proportions. So we will take two sample proportions and compare them. The difference between those two sample proportions will give us an estimate of the difference between the two population proportions. Because we can take multiple combinations and multiple pairs of samples from the respective populations, that then gives us a random variable, which is P bar 1 minus P bar 2. That random variable has a sampling distribution as long as the conditions for normality applies to both samples, which is N1 times P bar 1 must be greater than or equal to 5, and 1 minus 1 times 1 minus P bar 1 must be greater than or equal to 5. And 2 times P bar 2 must be greater than or equal to 5, and N2 times 1 minus P bar 2 must also be greater than or equal to 5. So as long as those conditions are satisfied, then we can approximate that sampling distribution of the difference between sample proportions by a normal distribution, which then gives us the Z values that you see right there. Okay? But remember that those Z values, there are two of them. One depends on whether or not in our null hypothesis we are assuming that the difference between them is 0. So we will have P1 minus P2 is either equal to 0, or P1 minus P2 is greater than or equal to 0, or P1 minus P2 is less than or equal to 0. So when we do the test, we will set in HO the value to 0. So that means that we'll be saying that the two of them are the same, the two proportions are the same, in which case then we have to use a single sample estimate. And so therefore we will pool the sample proportions to create a single proportion estimate. If now in the null hypothesis we are not assuming that there's 0, the difference is 0, so then for example we might ask, in terms of our example about investors in Ontario and investors in Nova Scotia, what if I was interested in finding out whether or not the difference between the proportion of investors in Ontario and Nova Scotia is greater than or equal to, or let's say greater than 2% or 3%, it doesn't matter what it is, but that it is greater than some value that is not 0. So now the difference between P1 and P2 is not 0. I cannot use a single sample estimate, so I will use the two sample estimates that I have for P1 and P2. That's the best I can do. And it will give us the second formula that I showed you, which is this formula right here. Okay? Good. So now it's time to work an example. So now for an example on inferences about the difference between population proportions. I want you to take a look at the question in our problem booklet, which is in chapter 10. I want you to take a look at the problem, problem number 36, okay? And read that with me, problem number 36. So we have winter visitors are extremely important to the economy of Southwest Florida. Hotel occupancy is an often reported measure of visitor volume and visitor activity. So Naples. Hotel occupancy data for February in 2 consecutive years are as follows. So we see the current year, our number of occupied rooms, 1470. Total number of rooms, 1750. The previous year, we had a number of occupied rooms of 1458. The total number of rooms this year, previous year, sorry, was 1800. So formulate the hypothesis that can be used to determine if there has been an increase. Now notice that's a very important term. If there have been an increase in the proportion of rooms occupied over the 1-year period. What is the estimated proportion of hotel rooms occupied each year? And then using a 5% level of significance, what is your hypothesis test conclusion? So basically, this whole problem is just about testing the hypothesis about whether or not there has been an increase in the occupancy rate, all right, over the previous year. So if you notice, we had 1458 over 1800, but now we have 1470, which is higher, over an even smaller number of rooms of 1750. So it will appear on the surface that there must be some kind of increase between the two. Since all of these 3 questions can be answered with our 5-step procedure, I will just go ahead and do our 5-step procedure. All right, so basically the question I will answer is there sufficient evidence that the proportion of, let's see here, that the proportion of rooms occupied has increased over the year, okay? So my hypothesis would be that the proportion of rooms occupied has increased versus it has not increased. So let's do step 1, our hypotheses. So HO, HA. Since I would like to show that the proportion of rooms occupied has increased, then my null hypothesis would be exactly opposite to that, which would be the proportion of rooms occupied has not increased. Versus the proportion of rooms occupied has increased. Okay? So proportion of rooms occupied has not increased versus the proportion of rooms occupied has increased. Well, if the proportion of rooms occupied has increased, then we're supposed to be able to show that the current year minus the previous year should be greater than or equal to 0. Sorry, it should be greater than 0. So we will say proportion of, let's call year 1 the previous year and year 2 the current year. That's one way to think about it. Or maybe it might be a little easier to just use C for current and P for previous. But the only problem is that P, if I use P as an index, it gets confused with P itself, which is the proportion. So I'm going to use 1 for previous, 2 for current. Okay? 1 for previous. So I'm going to make a note. 1 previous, 2 current. So in that case, then I'm looking at P2 minus P1 is greater than 0. And P2 minus P1 is less than or equal to 0. If it has not improved or increased, then that's what it should be. Okay? So that's the very first step. Second step is the test statistic. Now, if you noticed, in HO, the difference is 0. See? 0. So since we're going to assume P1 minus P2 is 0, then we're going to have to use the pooled sample proportion. So step 2, test statistic. Would be Z observed is equal to P bar 2 minus P bar 1, I have to be consistent, minus 0 over the square root of, and I could just put them in order. It doesn't really matter over here because we are using P bar. I'm going to factor out, P bar is common to the two terms in here, so we'll just to be consistent with the formula in your book. P bar 1 minus P bar, and we have 1 over N1, or let's call it N, yeah, N1, yes, 1 over N2, where really N1 is for the previous year, N2 is for the current year. Now, you might ask me, why didn't I put N2, 1 over N2 plus 1 over N1? It really doesn't matter in this case. If I have one before the other. But it does matter when I take the difference and how I interpret that difference, okay? So I'm hoping that you're okay with this. So that is the test statistic. Remember that if we're going to use a pool sample proportion, then we're going to have to take x1 plus x2 divided by n1 plus n2. All right? Good. Next step we want is the decision rule. Okay. And smaller. So step 3, decision rule. So the decision rule, is this a one-tailed test or a two-tailed test? So if you look at this carefully, since we want evidence that there's been an increase, that word increase should tell you that there's a direction. So because I'm taking P2 minus P1, then my rejection region would be here. Okay, in the right tail. This area is alpha 0.05. Since we're dealing with the normal distribution, then Z critical should be 1.64. 1.64, which means that if my Z value is greater than 1.64 or greater than or equal to 1.64, I will reject the null hypothesis. Or if the p-value is less than 5%, I will reject HO. So the nice thing is that all of these steps, we've been doing it now for quite some time, and they're all consistent. It's the same thing. What changes over time is really the test statistic, all right, and the context of the problem. So now we have our decision rule. The next step is to go ahead and do our calculations, which is our analysis. So step 4, the analysis. Let's find our sample proportion. So for the previous year, which is P bar 1, we were told that we had 1458 rooms occupied over 1800. That turns out to be 0.81. In the current year, P bar 2, we have 1470 rooms over 1750. It turns out to be 0.84. So just on the surface alone, you could see that there's been an increase in the proportion of rooms occupied. Since we're going to need the pool sample proportion, let's go ahead and find that. So P bar would then be 1458. We add, that's our x1, plus 1470 x2 over n1 plus n2, which is 1800 which is 1800 plus 1750, and that turns out to be 0.82. So now we have the pool sample proportion, but we have the individual sample proportions themselves. So what we now need to do is to calculate the value of the test statistic. Let's do that. So Z observed will be 0.84, which is our P bar 2, minus 0.81, which is our P bar 1, minus 0 from the null hypothesis. And then we have 0.82 times 0.16, 1 over 1800 plus 1 over 1750. It turns out that that is equal to, I think I could squeeze it in over here, 2.33. All right, 2.33. And you may recall, some of you may recall that 2.33 is when you have 0.02 in the tail of the distribution. Sorry, 0.01. 0.01 in the tail of the distribution, right? Because that's like a 98% confidence interval. Yeah, 0.01, 0.01, and the Z value is 2.33. But you don't have to remember it that way. We need to find the p-value. So p-value is the probability of observing the sample evidence. What's that sample evidence? Is 2.33, but or evidence that's even more extreme or even more opposing of the null hypothesis. So that would be greater than or equal to 2.33. And it turns out that when we look up table, that would be 0.01. Or, that's what it should be. Or if we look at 0.0099 is probably a more accurate measure, 0.0099, which basically rounds up a little bit to 0.01. Okay, so given that we have our p-value, we have our test statistic, we have our critical value, the only thing left to do now is to apply the decision rule. Step 5. And here we go. Step 5, the decision and the conclusion. Decision conclusion. So since my decision, since 2.33 is greater than 1.64 or I could say, and that's a critical value approach, or p-value approach would say, or since 0.0099 is less than 0.05, that's basically our p-value is less than alpha, we will reject the null hypothesis. What do we conclude? We have sufficient evidence sorry. The occupancy rate has gone up. Essentially, we have a higher level of occupancy over the year, right? Or greater, there's been an increase in the occupancy rate over the year. That we have evidence that that we have sufficient evidence the occupancy rate has increased over the year. Now, I know I didn't state it exactly how I stated my hypotheses. I should have said the proportion of rooms occupied has increased, but that's the same as the occupancy rate, proportion of rooms occupied. So I've just basically restated it, but in a manner that is still consistent. We have sufficient evidence that the occupancy rate has increased. What kind of error might we commit? So we have a possibility of type 1 error, since we rejected the null hypothesis. Type 1 error. Possibility of type 1 error. And it turns out that the probability of type 1 error is the p-value, 0.0099. Okay? That is it. So that's the hypothesis test right here. I'm going to extend this a little bit and say, find me a 95% confidence interval for the difference between the population proportions. So I'm going to add to this. So we do both confidence interval and hypothesis testing. Find a 95% confidence interval for P2 minus P1. In other words, the difference or for the increase in occupancy rate, or for the difference in the occupancy rate, P2 minus P1, that is the difference in the occupancy rates. So in this case, it will just be, I'm going to keep my order, which is P2 minus P1, P bar 1, plus or minus the critical value times the standard error. So we have P bar 1, 1 minus P bar 1 over N1, P bar 2, 1 minus P bar 2 over N2. Substituting our values, we get the following: 0.84 minus 0.81 plus or minus, since it is 95% confidence interval. Actually, let's use 95%. Okay, let's use 95%. 1.96. And what do we have? Times, we put all of our values in there. 0.84 times 0.16 times 0.16 over 1750, and then we have plus 0.81 times 0.19 over 1800. So continuing from where we left off, we are now trying to complete this confidence interval. So what we have is 0.03 plus or minus 1.96, which comes from the critical value based on a 95% confidence interval. And the value of the standard error is this piece right here, which is 0.012739. When we multiply that, that becomes 0.03 plus or minus 0.025. So plus or minus 0.025, I think that will give us a difference between the proportions of P2 minus P1, since that's what we got the differences for, will be 0.055, and this would be let me see here, which would be 5 from that would be 5.005. Okay? So if we look at that confidence interval, all the differences in that interval is actually positive. All of them, they're all positive. And so in that regard, P2, we have evidence that P2 is greater than P1, which means that there has been an increase in the rate. So just think about this for a moment. How do we interpret this difference? Any value in that interval turns out to be positive. And for you to get a positive difference, the only way you could get a positive difference by is for P2 to be greater than P1. Which means that the proportion or the occupancy rate after, or during the current year, is actually better than the occupancy rate in the previous year. So we have evidence that if somebody were to ask you to interpret this confidence interval, we do have sufficient evidence that the occupancy rate has actually improved or increased, because any value in that interval is actually positive. If this was negative, then we would not have enough evidence, but it's not negative, it's actually positive, and therefore we have sufficient evidence that there's a difference between the two things. All right. So just to kind of summarize what we did today, we went over the topic of inferences about the difference between two population proportions. In the first place, we did a hypothesis test involving the difference between the two proportions. We have two conditions to consider. One, where in the null hypothesis, we actually will assume that the two population proportions are the same, in which case P1 minus P2 will be set to 0. If that is the case, then we cannot estimate a single value with two different sample proportions, so we must merge them into a pooled sample proportion P bar. And so we combine the two samples, X1, X2 over N1 plus N2. So that then gives us that single sample estimate or pooled sample proportion P bar. And we use that in our estimate of the standard error. If instead we had, in the null hypothesis, basically stated that there was a difference between the two proportions that was non-zero. And so I gave you the example of if we're looking at investors between Ontario and Halifax, or if we look at the problem we just worked, if there was a difference of at least, let's say if we're interested in showing that the occupancy rate had gone up by 1% or more. If we were interested in looking at that, then the difference between the two is non-zero. We would have to consider, excuse me, the second formula, which basically allows us to use the individual sample proportions as estimates. Okay? And so the value of the difference in that case is non-zero. So we would have to use the two individual sample proportion estimates that we got. Good. So your turn to try a problem. And I believe there is one, let's see here if there's at least one more that you can do. No, there's a simple one. If I would look here, if you want to just test yourself. So prior to the question that we worked, there is a question here that is asking us to find p-value, and so on. So if you look at that question, you have P1 minus P2 is less than or equal to 0, P1 minus P2 is greater than 0, and we're being asked to kind of, what is the p-value in that case? There's also another problem here, which maybe this one is the one that you could try for your self-test, which is number 30, right? So what we have here is that a Business Week Harris survey asked senior executives in large corporations their opinions about economic outlook for the future. One question was, do you think that there will be an increase in the number of full-time employees in your company over the next 12 months? In the current survey, 220 of 400 executives answered yes, while in the previous survey, 192 of 400 executives said yes. So provide a 95% confidence interval estimate for the difference between the two. So that one is a confidence interval estimate. And then you could go ahead and say, okay, let me use the same significance level and do a hypothesis test whether or not there's been an increase in the improvement in the economic outlook and so forth. Good. So I leave that for you to try, and then for you to ask me questions on whether or not you did it appropriately. Okay? See you next time. Bye-bye.